Hi, my name's Raj Joshi. I'm a physics teacher from South London. Today I'm going to talk to you about nuclear fusion and nuclear fission. This is aimed at A-level students. The topic does fit into the GCSE, but we're going to go into far more mathematical depth with the A-level course. What we'll do is we'll go through some of the content, and there'll also be 2 exercises for you to do to recap your knowledge and show you understand the content. Let's start off with the idea of conservation of mass. This is probably something your chemistry teacher drilled into you at GCSE. If we've got something that's got a certain amount of ingredients and we weigh them all, and then we work out the thing that's being produced, it should have the same amount of mass as the ingredients. In chemistry terms, the product should have the same mass as all the reactants. And this is a fundamental law of chemistry. You can't have mass appearing from somewhere or disappearing to anywhere. The amount of mass before and after a reaction needs to stay the same. With that in mind, I'd like to introduce you to the concept of a unified atomic mass. This will be defined on your formula sheet with a lowercase u. 1 u is defined as a 1/12 of the mass of a carbon-12 atom. So carbon-12 is made out of 12 things in the nucleus, and we divide that mass by 12. So we've got 12 things in the nucleus, 6 protons, 6 neutrons, and if we divide it by 12, we should get roughly the average mass of the protons and neutrons. So on your formula sheet, 1U is defined as 1.661 times 10 to the minus 27 kilograms. And if we multiply that value by 12, we should get the mass of a carbon-12 atom. So we should be able to work out the mass of a carbon-12 atom by multiplying U by 12. So we get a value for the mass of a carbon-12 atom, 1.9932 times 10 to the minus 26 kilograms. We also know the mass of a neutron and the mass of a proton. So with 6 neutrons and 6 protons in the middle of the carbon atom, remember the electrons are really tiny, so we can ignore them for now. We can say that 6 times the mass of the neutron plus 6 times the mass of the proton is 2.0088 times 10 to the minus 26, a different number from the value that we had with 12U. So we've got a very small amount of mass, but still a significant amount, missing. That's a problem. That breaks the rules that we said our chemistry teacher taught us at GCSE. So we need to find a solution to this. A solution could come from the gentleman in the bottom left. If you ask a non-physicist to name a physics equation, a lot of them will come up with Einstein's E equals mc squared. E being energy, m mass, and c is the speed of light. This gives us a way of converting mass into energy. So we could use it to deal with this amount of mass that doesn't seem to stay constant. So if we take the change in mass, 1.56 times 10 to the minus 28 kilograms, chuck it into this equation with the speed of light being 3 times 10 to the 8, we get a value for the amount of energy. 1.404 times 10 to the minus 11 joules. A tiny amount, but we are dealing with individual atoms here. When we express it in mega electron volts, we see there is a significant amount. What does that quantity of energy actually represent? When we first teach about the structure of the atom, we'll often talk about protons and neutrons being in the center of the nucleus. Those protons are positively charged, so students will ask, how can they be in the nucleus if they're all repelling each other? And your teacher will have given you the explanation that somehow these protons are sort of stuck together. There's some kind of force sticking them together. They may have mentioned gluons. When you came into A level, you'll have started to talk about the strong nuclear force. This force that keeps all of the things in the nucleus together. We can move on to talking about this as needing a certain amount of energy to keep everything bound together. We refer to this as binding energy. Each of those nucleon within the carbon-12 nucleus has 7.3 mega-electron-volts of energy per nucleon to bind it together. We call this the binding energy. If we graph the binding energy per nucleon for different elements, we get this shaped curve. You can see that hydrogen, which has only got one nucleon, doesn't need any binding energy. It doesn't need to be stuck to anything. But as we go further and further up, we need more and more binding energy to keep things together. The thing that has the most binding energy is iron 56. After that, the amount of binding energy goes down. And as we go towards really, really heavy nucleus, then we get to things like uranium, which isn't that strongly bound together and can be unstable. In most exam specifications, we have this graph of binding energy per nucleon on the y-axis and the size of the nucleus in terms of numbers of nucleon on the x-axis. And the binding energy per nucleon all take positive values. Now, this is an interesting one to think about. We've got this binding energy per nucleon. It's something that's keeping the nucleus stuck together. So it's almost like a potential well. It's almost like a hole that the nuclei are in, and it's the amount of energy that we need to put in to take them out of that hole. So I often have debates with my students about whether or not this should be a positive or a negative number. We sometimes think about a ball sitting on the surface. So that ball sitting on the surface would have a gravitational potential energy of 0 joules. It's just sitting on the ground, it's at 0 height above the ground, so it has a gravitational potential energy of 0. But let's take that ball and put it into a hole. We can think maybe this is a bit like a golf ball going into a hole in a golf course. How much energy has it got now? Well, it had 0 joules on the surface and it's gone into that hole. Some people might say it's got a negative amount of energy. And in some examination specifications, we'll see this binding energy per nucleon curve being the opposite way around. And we can think of it as almost like a potential well. A hole that these nucleon are sitting in. And the binding energy is the amount of energy that we need to separate out each of those individual nucleons and bring them sort of infinitely far away from each other. So this graph shows us that iron 56 has the most binding energy. The nuclei within iron 56 are sort of the ones that are furthest into that hole, that need the most energy to take them out. And anything that's got a lower binding energy than iron 56 isn't quite as tightly bound as iron 56. So if we've got iron 56 here, everything to the right of it isn't as tightly bound. So these really, really big nucleuses would release energy as they move towards iron 56. Now in practice, for a big nucleus to get smaller to get into iron 56, it needs to split. And we call that splitting nuclear fission. So if we've got something very, very large, it will split up into smaller things. And those smaller things, as long as they're still bigger than iron 56 will decrease in binding energy, so that energy will be able to be released. On the left hand side, we've got some things that are lower than iron 56 as well, and the process to get up to iron 56 is called nuclear fusion. So we've got smaller things, and they'll have to join together to fuse to get larger, all the way up to iron 56. So these two processes will be the nuclear reactions that can generate energy. Things splitting up is called fission. Things sticking together is called fusion. You'll notice the curve is a lot steeper on the left-hand side, the fusion side. And so there's a lot more energy that we can get out of nuclear fusion than nuclear fission. Nuclear fusion is what stars use to generate electricity. But in practice, in man-made situations, nuclear fission is what we use in everyday life, in nuclear reactors. It's also what powers nuclear bombs. Nuclear fusion does exist in man-made situations, but it's still at the experimental stage at the moment, although we've seen some fairly successful prototype nuclear fusion reactors. We've just covered three new terms: binding energy, nuclear fusion, and nuclear fission. And we've got this binding energy per nucleon graph, which can explain how these things work. Take some time to think about these new terms. What do they mean? Why does nuclear fusion occur, and why does nuclear fission occur? What are the conditions in which they occur? Binding energy is an amount of energy. It can be measured in joules or electron volts. But there's some arguments that maybe it should be a negative number, even though it isn't on the binding energy per nucleon graph. Pause the video and take some time to make some notes in order to explain to yourself what these terms mean and how they're linked. We can use the binding energy per nucleon curve to work out the amount of energy released in a nuclear reaction. Let's have a look at a question. So this tells us that there's two deuterium atoms and they're fusing together to form a helium-4 atom, and we need to work out how much energy is released. Deuterium is an isotope of hydrogen. It has a neutron as well as a proton. So on the binding energy per nucleon graph, it's written as H2. So we've got two of these H2s, two deuteriums, and they're fusing to form one helium. So let's have a look at how much binding energy per nucleon they have. So here's the helium in green, and here's the deuterium in blue. So if we read off that graph, our deuterium is something like 1.1 mega electron volts per nucleon, and it contains two nucleons, so we need to multiply that by 2. That's a common mistake that people tend to make, is forgetting to multiply it by the number of nucleon. And we need to multiply that again by 2 because we've got two deuterium atoms. With helium-4, we've got a binding energy of nucleons. It looks dead on 7, I'd say, but we need to multiply that by 4 because we've got 4 nucleon. So we're going from 4.4 mega electron volts to 28.0 mega electron volts. Quite a big jump. So the difference there is 23.6 mega electron volts. That's the amount of energy released in that one reaction. In a star, we have a whole sequence of nuclear fusion reactions. So two hydrogens will fuse together and form a deuterium atom. That will fuse together with another hydrogen atom to form helium-3. And then two of those helium-3s will fuse together and give off two hydrogens and one helium-4. Work out, using the binding energy per nucleus curve, the amount of energy released in each of these reactions. Then add them all together to work out the total amount of energy released for those 4 hydrogen nuclei that we started off with. Once you've worked out the amount for 4, you need to scale this up, because in a star there will be 10 to the 57 hydrogen atoms. Work out what the total amount of energy that will be released by the star during its lifetime. Pause the video and have a go at this calculation. We can use a similar method to calculate the amount of energy released in a fission reaction. So we're asked here, what's the amount of energy released when uranium-236 splits up into krypton-92 and barium-141? So let's write that down as a nuclear reaction. And let's start by drawing some lines on our graph to work out the binding energy per nucleon. So we've got uranium here in red, krypton in green, and barium in blue. Now uranium is going to give us, let's read that off the graph, about 7.5 mega electron volts. Krypton is going to give us 8.7 mega electron volts, and barium about 8.6 mega electron volts. So we've got a bit of a difference between what we start off with in terms of binding energy and what we end up with. So we should get some energy released. Not quite as much as with fission, because the slope isn't quite as steep. So let's multiply those values by the number of nucleon to get these values, and then we can calculate the difference. And we've got 243 mega electron volts. Now the gap isn't as large, but we have far more nucleon, so we get a substantial amount of energy again. I hope you found that useful. My name's Raj Joshi. On behalf of the Science Learning Partnership, good luck and goodbye.